Okay, good evening, everyone. We'll be starting the class. So, welcome to the week two of the live interactive session of the fabrication techniques for MEMS-based tensor, a clinical perspective. This is being taught by the course instructor, Professor Hardik Jitendra Pandya of IISc Bangalore, and I am the PMRF teaching assistant, Vikas Pandey from IIT Jodhpur. This is a brief about me. For more details, you can visit my portfolio, and the schedule of the classes will normally be Tuesday 6 to 8 p.m. and the link will remain same. And recording of all these are available on the YouTube channel mentioned here. And to reach me, you can also write on this email. So before going towards problem solving, I'd like to ask if you have any doubts regarding anything taught in the class. Please feel free to ask. You can unmute yourself and speak. And during this whole session, I will not be seeing the messages, so you can respond by simply unmuting yourself and asking and speaking up. Okay. So if any doubts, please ask. Any doubts or anything you are not able to understand, you want some clarification in that, you can ask. Anyone? You can hear me, right?
No doubt, Vikas. Please, Dr.
Okay.
Vikas, you can continue.
Yeah, sure. Okay. So Uh, let's come to problem one. That is wafer flats. Remember in the previous class also, we saw that if it is a wafer, it will have some flats like cut marks, some with 45 degrees or 90 degrees cuts. Okay. The angle between primary and secondary cut, if present, flats of a silicon wafer indicates which of the following: crystal orientation, dopant type, doping concentration, or wafer production technique. Anyone? Yes, please.
Dr. Vikas, actually, I haven't
Yeah,
attended that session, but still,
yeah,
I am
yeah, no
eagerly
problem.
waiting to know how, if it's
Yeah,
possible for you to explain how to,
yeah,
I
yeah.
mean, work out regarding this plane. I mean, with the cut, how can we recognize this is the plane 110 or 001
Yeah,
like that?
sure,
If possible,
sure, I'll
then
do. Yeah, sure, I'll do. And one thing, I am still not a doctorate. I am pursuing PhD. So,
oh my God.
yeah.
Yeah,
So,
Vikas.
yeah. Uh, So let's wait for some time so that someone else can also try. Then we will discuss that. I have put that in.
Fine, fine, fine.
Okay. Anyone
Thanks.
else who would like to answer this question?
Sir, I guess it should be either dopant type or doping concentration. I'm not sure.
Dopant type, doping concentration. Any other answer? See, like to it is just that we think only one answer should be correct, right? That is why I have put some questions in which multiple answers can also be correct. In fact, mostly I'll be putting questions like that. So feel free, you may be partially correct. Okay. So you can answer, and there can be more answers than this. These two are correct. Very fine. Okay. Anyone else? Okay. So let's go to C. Like you remember this, I saw I showed you this in the previous class also. So generally, when we procure the wafer, there are two things you will see. First is that they are circular in shape, and there is one polished side. In general, there are wafers which will have both the sides polished, like they will be shiny. There are such wafers also, and in MEMS, mostly we use both side polished wafers. But if you buy a general wafer, silicon wafer, it will be one side polished and circular in shape with some cut marks. Okay, so the cut marks signify, see, if they are opposite to each other. One is a bigger cut mark, one is a smaller cut mark. If they are opposite to each other, then it is 100 N type. So you see, it is specifying this 100. That is the which option? Crystal orientation. Okay, and the other one is N type. By N type, we mean it is doped with something that have more electrons, right? And N type or negative type, we can say, having more electrons. So it is orientation as well as uh, dopant, dopant type. Okay. Similarly, if we go to the second one, that is by 90, if these flats are at 90-degree angle, then it will be a P type of 100 silicon. Okay. Again, here also 100 is the orientation and P type is the dopant type. Okay. So crystal orientation and dopant type, these are correct for sure. Okay. Then if it is uh, separated by 45 degree, like one big flat and another flat just adjacent to each other, it is 111 N type. And if only one primary flat is there, that is simply 111 P type. Okay. So what information we got from here is crystal orientation and dopant type. Clear? Any doubts? I'm expecting one simple doubt here, if anyone is paying attention to it. Hello, Varsha, you got it?
Yes, sir, but I'm not sure why doping concentration is not the right answer.
See, the doping concentration is something about, you see, how many molecules of dopant are put there. Okay. So if this is N type, okay, if it is doped with say 10 to the power minus, not minus 10, sorry, 10 to the power 13 atoms, or if it is doped with 10 to the power 15 amount of atoms, still it will be an N type wafer, right? And it will still be shown by the same type of cut. That is why
Got it.
doping concentration is not mentioned here. And one more thing is that orientation. Are you clear with what is orientation? 100, 111, I am telling. Is
Yes,
that
sir,
it?
yes.
You are clear? Yes, you are from electronics background, right? Anyone else who has any doubt what is this 100 or 111? Okay, I think everyone knows. Okay, so now let's come to in e-beam evaporation technique, the current density leaving the filament.
Vikas, may I ask one question in between?
Yes, 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 sure.
If you are having a silicon, intrinsic silicon, then what about the cut?
There will be no cut in that. And
That's fine.
but in general, we cannot buy intrinsic silicon. If you go to a fab, that is very difficult to manufacture, and like that is very rare. That is why we don't discuss that.
Fine.
Yeah. So in e-beam evaporation technique, the current density leaving the filament can be formulated as Gauss equation, Maxwell equation, Richardson equation, or Faraday's law. Anyone?
Maxwell's equation.
Maxwell's equation. Okay. Anyone else? Anyone else would like to add? Okay. The correct answer is Richardson's equation. Um, kindly check, like I think I had kept that. Just I think I had kept that equation also. Yes. Okay, it was not. So this is the Richardson-Dussman's equation. You check the parameters. This is the correct equation to estimate this e-beam evaporation current density. Okay. Now let's come to like that was a bit technical. Let's come to some practical aspects. Okay. E-beam evaporation technique e-beam evaporation is a physical vapor deposition technique. Physical vapor deposition technique in which the target material is bombarded with an electron beam in a high vacuum chamber. Is it true or false?
Yeah, it's true,
False.
no?
Yeah, it's true. So why we are calling it as physical vapor deposition? Because here, if we see how this e-beam works, it is mostly like an electron is coming, it is bombarded over it, and it forces the uh, material to move. Okay, there is no chemical reaction involved. We can just assume that it is moving from one place to another, like from one target to the sample. Okay, that is why it is physical vapor deposition. Remember that deposition techniques are divided into two parts: physical and chemical vapor deposition and chemical. And there are different varieties like physical, under physical e-beam, thermal, sputtering. There are a lot of things, and chemical CVD and other ones are coming. Okay, so this is true. So coming to problem 4, this is about the general way of fabricating. In the previous week also we saw that we want to create a micro heater structure, like which will heat that localized area, and then we want to insulate it using silicon dioxide layer. And here the condition is given that only silicon wafers are available as substrates, like they are not pre-oxidized. In the previous class we saw that if we directly use silicon, it and on it if we deposit metals, it will be difficult, since the silicon will also take part in the conduction, and we don't want that to happen. So what we are doing is that we have silicon dioxide over it, SiO2, and then over it we put the metals, we pattern it as per our requirement, and then again we cover it with SiO2 passivation layer. Okay, so to do this, which of the following processes in which sequence will be used to fabricate the devices? Anyone? Which of the processes will be used and in which sequence? You can try at least list out the processes, then we can discuss the sequence.
I think we should start with PCVD, no?
PCVD, okay, for silicon
And
dioxide.
and it is
Hmm.
clear that at last we go for the ellipsometry to determine the thickness.
Okay, thickness determination. Okay,
That is at last.
okay.
And lithography, then thermal oxidation, metal deposition.
PCVD, then lithography. Lithography will be two. Then thermal oxidation.
Then then metal deposition,
Okay, so
and
this is
then
the sequence.
ellipsometry.
Okay. Anyone
I
else?
think so.
Yes, fine. Anyone else? I think like the understanding is fine, but some sequences just one. Yeah. Anyone else would like to add or change the sequence? Yes. Okay. Let's understand the difference between uh, this upper SiO2 and the lower SiO2. Both of them are silicon dioxide. First one is grown from the surface. Like when we are talking, we are saying it is grown. Okay, so this is grown, and then the one is deposited over. First one is grown, like something is there. You are doing some processes, and a layer will grow over it. Okay, so this is a grown oxide. Then the last one is a deposited oxide. Okay, so there is a slight difference between these, and this slight difference will have a lot of effect on the quality of this silicon dioxide also. So the lower one, since we already have silicon, it is grown. Okay, so the first process in this whole thing will actually be uh, just- will actually be this one, thermal oxidation, because we will grow the silicon dioxide first. Then is we want to make the pattern, and these patterns are to be made using metal. So it will be deposited. Okay. So the next one is metal deposition, which can be either done using thermal evaporation, or it can even be done using sputtering. It depends on what system or what facility we have, or e-beam, anything. Okay. Then it's we need to do the pattern. We need to pattern this metal for our heater. So that in that case, wherever patterning is there, we will use lithography. Lithography is one of the major you can say one of very important steps in all the processes, because sometimes multiple layers of lithography we have to do, and it is a very sophisticated process also. That is why this is one of the most important processes in this MEMS and microfabrication. Okay, so next will be this lithography, and then will be the PECVD of silicon dioxide. So it was just reversed, like instead of thermal oxidation, like thermal oxidation will not be done later, but thermal oxidation will be done when silicon is present. Oxidation means it will grow from silicon itself. That is why uh, it is done at first, and later on when we have to put something over it, since we don't have silicon now, we have the metal contacts and all, and if we try to do thermal oxidation at this stage, these metals will melt, and we will not have the desired patterns. That is why now we will go for colder processes, that is PECVD of silicon dioxide. Okay, and then yes, we can go for uh, this one, ellipsometry, to measure the thickness, but that is actually not the part of fabrication, so I had not kept it like in that. But still, yes, it can be done once everything is done. Okay, and ellipsometry can even be used after this thermal oxidation also, like to measure the thickness. Okay, any doubts in this?
No, sir.
Clear? Okay. So actually, they are given in sequence only: thermal oxidation, metal deposition, lithography, and PECVD of silicon dioxide. Ellipsometry will be done here as well as here, but that is not an important step of the fabrication. It is a technique to determine the thickness of silicon dioxide layer deposited. Okay, it is a characterization technique, we can say. addition technique. And what is it used for? To measure thickness of mostly dielectrics. Okay. We cannot measure the thickness of metals using it since they are opaque in nature. Like if they are, there is a small transparent, not perfectly transparent, a translucent film is there, we can measure the thickness of it using ellipsometry. Okay, which of the statement is correct for HMDS? This is used before photoresist coating to increase adhesion of photoresist. H HMDS layer is generally very thin compared to photoresist. It is an etchant that increases roughness of substrate surface, increasing adhesion of photoresist. It is used to change the optical property of photoresist so that photoresist can be exposed during light of another wavelength. Which of the following is correct? HMDS, anyone remembers where is it used? In lithography, like it is used in lithography process. Anyone? Have you heard of primer? Like whenever we get our home painted, okay, in that we use something called as primer. Have you heard of it? Anyone? Anyone have seen like when a room or even a wooden wooden chair or table is made newly made, there is something called as primer that is used over it, and then a paint is applied over it. Anyone who knows that, like who have seen this thing? No one? Are you sure? No one have seen like a primer being applied before a paint?
I think answer may be between A and C, not sure.
A and C. It is used before. So yes, very fine. So
Yeah.
like you are getting the idea, right? And then it is an agent that increases the surface, okay, and is generally very thick compared to photoresist. Is this also correct? So this is correct. Also, the first one is correct, right? It is very similar to a primer, okay. And why is it done? Because generally what happens is that when we have this the wafer on it, some metal is deposited, and in uh, this metal will have not have that you can say that smoothness to have a very good layer of photoresist over it, as well as in that case the photoresist will not stick properly. So to increase the adhesion, like to fill those ups and downs, just like we use primers, it is a very not thick, like a very thin kind of liquid, just like primer. If we compare it to the paint, it will be very like it will not be thick in texture. Texture it will be watery kind of thing. Okay, so HMDS is also very thin textured substance that is used to fill up that, and it acts as an adhesive to the photoresist, and it is very thin, and it so it will not disturb our whole setup. And if we pour over it and then we put the photoresist, it will properly stick. But this is something that is not generally used. It is only when you are having adhesion problems, or when you want a very good adhesion to happen, then you are using. You can even skip this HMDS and still the process occurs with slight, like not that perfection that we wanted, but still we will get it. Okay, so this one is the correct answer. It is an etchant that increases roughness of the substrate. This is not right, because if it will etch, and first thing is that we don't want to increase the roughness, we want to decrease the roughness. Okay, we want to decrease the roughness so that it will, like, we are not trying to put something in bulk, we want a very thin layer of it, thin layer of this photoresist to be on the top. That is why we don't want it to be very rough. We want it to be very smooth, so that if when we put it and when we spin it, it spins very uniformly and goes throughout the and makes a very uniform thickness, so that we can expose it at one go. That is why we want smoothness, not roughness. Okay, increasing the addition of photoresist. So this is wrong, and it will not change the optical property of photoresist. If it does, we will not get the desired results. So the correct answer is 1. So very good. Okay, so let's move to the next question. Okay, and this is a very important question, that when we talked about that, the first process was thermal oxidation, that is growing oxide out of silicon wafer, and there are two methods to do that. Thermal oxidation can be done using two methods. One is dry, another is wet. Anyone can say what is the difference between dry and wet oxidation? Yes. Anyone can try
I
to.
think in a dry oxidation we are not using water vapor, and
Yes.
in wet testing we are using H2O as well. I think that nitrogen is a purge and oxygen.
Oxygen, yes. So when we are talking about oxidation, certainly there will be oxygen. But along with that, we are like we are getting, in case of dry, we are getting the oxygen directly from oxide. Oxygen, sorry, like we are getting the oxygen molecules directly from oxygen. In case of wet, we are getting it from H2O. See this, there is H2 and O. Okay, and which one is faster? Anyone?
Uh, mm, Dry, I think dry one is faster.
No, that's opposite.
No.
Because if we see it, like,
It is faster, 10 times faster. Wait.
yes, wet is faster. Why wet is faster? Can you think, like, why wet is faster? If you see these two molecules, okay, when we are talking about oxygen, it is always O2. Okay, O2. If we see the mass, or in like, if we see the thermal oxidation process, if suppose that some oxide has formed here, okay, and now this is the surface between oxide and silicon. So the next oxidation will not occur on the top, because there is no silicon that has to be converted into oxide. So this molecule O2 or H2O, whichever is there, that have to go and react here, go inside. So a smaller molecule will be able to reach there very easily. So if we compare the size of O2 and H2O, H2O will be much smaller in size, because hydrogen is having very small size compared to oxygen, right? Yes, are you trying to say something? Yeah. So if we see that when we have two molecules of oxygen, and here we have actually, not sorry, two molecule, two atoms of oxygen, and here if you see, there are two hydrogen and one oxygen. Still, if you see its mass as well as its size, will be very small compared to oxygen. That is why dry oxidation is slower. But along with that, we have one other problem also, that is, uh, dry oxidation is of very good quality since there is no other byproduct and all. And in case of wet oxidation, it is not of that good quality because this hydrogen has to be released. It will come out and it will create some small pores that will not be of good quality. Okay, so this was something related to like oxidation, dry and wet. So in both these processes, some silicon will be consumed and silicon dioxide will be made. Like if we have this whole silicon and if we heat it in presence like at almost around 1100 degrees Celsius in presence of oxygen or H2O, okay, then what happens is that this oxidation occurs. If it is O2, it will be dry. If it is H2O, it will be wet. So in both the cases, some part of silicon is utilized to make the silicon dioxide. So if we have got a oxide of, we have to get an oxide of 750. Yes, Dhananjay ji, yeah.
Because I do have one question. Actually,
Yes, sir.
we are using either horizontal furnace or a vertical furnace for the, you can say, deposition of this oxide. So
Yeah,
where we are, the temperature is around 1100 degrees Celsius, and if we
yeah.
are passing oxygen, then what
Mhm.
about the chances of fire?
It is very closed. It is not that like we are using oxygen, and the problem is that the thing is that when we talk about fire, oxygen is not the thing that will burn. Oxygen just helps in fire. It is not the thing that will burn. There is no other thing. Like it is properly purged first. Like we create a vacuum kind of thing there, and then we pass oxygen. If it was hydrogen, purely hydrogen was flowing through it, it would have created a fire certainly.
Oh, okay, thanks.
Yeah. Yeah. So what if we are creating a 750 nanometer of this oxide layer? Okay, let's say by dry oxidation and wet oxidation, two different ways. Okay, so what will be the thickness of oxide being used to create 750 nanometer of oxide? Sorry, I said, yeah, what will be the thickness of silicon to create 750 nanometer of oxide using dry oxidation? And what will be the thickness of silicon to create 750 nanometer using wet oxidation? The first one, like first value is for dry, second value is for wet. Can anyone answer?
345, 0.46 x
0.46 of the value 750 nanometer, right? So if we go, we do this, what is the answer? 345 nanometer, right? And for both the cases,
Yes, sir.
okay. And can you tell me from where this 0.46 came? Yes, it is shown there, but anyone have idea why this 0.46? Anyone? This
Sir,
is very correct. Yeah.
thickness of silicon by
Hmm.
thickness of SiO2,
Hmm.
the relative molecular weight
Hmm.
and density, we can have the value of 0.46.
Yes, exactly. So it comes from the if we yeah, like this is a general formula. Uh, somewhere it is 0.44, somewhere you will get 0.46. Both are fine. Okay, slight difference. So if we see silicon, silicon is having atomic mass of 28. Okay, and oxygen we are getting atomic mass of 16. So SiO2. So what will be the atomic mass of it? 28 plus 32, which is how much? Yeah, 60, right? 16. So if we compare it with silicon, so like 60 by 28, how much it will be?
Two.
How much?
2.1 something, 1.
2.14. That is the so I'm talking in the opposite way, that the amount of silicon that is consumed, 2.14 times the consumed silicon will be the SiO2, right? So times the silicon consumed. Now if we reverse it, like 28 upon 60, we will get this value, what we are getting here. Okay, 0.46. 4 somewhere, even it's given, it should be 4.6. More precisely, if we go by that, it will be 4.6. Okay, so this way, and these are the two equations that are involved when we go for wet and dry oxidation. So which one is better? Anyone? And like, what should we go for? Like, if we are given a chance, should we go for dry oxidation or wet oxidation?
Dry oxidation.
Dry oxidation. But dry oxidation has one problem, that is time. Since it takes a lot of time, so what is generally done is that since we want the interface here, where it is connecting the silicon and SiO2, like that is, in fact, many times you will hear that it is a God-made interface, very well made. You like one of the best interfaces in semiconductor industry. Other metals and this, we are struggling a lot to make it adhere. Okay, but to have a good quality of it, what we do is that on the top level and at the bottom level, we want good quality of SiO2. So in general, what is done is that it is done as the process dry, wet, dry. So don't think that when we are talking about dry oxidation, the whole process will be dry only. When we are talking about wet, the whole process will be wet only. It's not like that. In practicality, what is done is that the top surface we want good, so we start with. Sorry. Hello, am I audible now?
Yes, Vikas.
Yeah. Sorry, actually, there some power cut has happened. I don't know why. Just a minute. Okay. Okay. So we can continue. We- Okay, my screen is now visible to everyone. Yeah. Now my screen is visible.
Yes, it is.
Yeah. So as we were talking, in general, what happens is that instead of doing fully dry or fully wet oxidation, we go for dry, wet, dry. This is the general process that is followed. That will ensure that on the top, above it, we have to make the structures, right? So we want a very good layer that has less defects. But certainly, if we are doing wet after it, some defects will anyway arise, but it will not be of that lower quality. Since we want good quality, we can go on for uh, like longer time than wet, so that we can go faster. Like in between, in the central part, we can go for faster oxidation, and then again when we are about to reach the end, we go for dry oxidation. So this is the general way that is done, and these are the two reactions. And here, in the case of wet, this H2, this is the thing that actually degrades the quality a bit. Not, we can not say very much, because hydrogen molecule is smaller in size, but this is the advantage also when we are using H2O, that since this molecule is smaller in size, it will be able to reach or diffuse to the interface easily. So this is fast but lower quality. In case of dry, it is slow, high quality. But in both the cases, if you see, the output is same, SiO2, single molecule of SiO2. That is why the thickness that will be generated will still remain the same. If we are using one Si, the output is one SiO2. There is no increase. That is why here, first thing is that this can be correct or this can be correct. This cannot be correct, this cannot be correct. Why? Because there are differences. And if we calculate using this 0.46 into 750, we'll get that it is 345 nanometer. Okay. Any confusion till here? Okay. So let's come to the next question. Why is vacuum created in the chamber before thermal evaporation? This is something a very cumbersome thing. Every time whenever we have to do thermal evaporation, we uh, create a very high vacuum in the chamber, and that takes a lot of our time. Okay, but why is it done? Is it to increase the mean free path of evaporated molecule, to get a film with more purity, to prevent oxidation of evaporated metals, or all of this?
I think we go for all of this, no?
All of this, yes. So, can anyone try to explain what is this mean free path? Increasing the mean free path.
The path, between the successive collision of
Yeah,
our
very
evaporant
right.
material before they reach to the target.
Yes, very right. So, we want that there is the least number of collisions. In fact, we want that ideally there should be no collision between our uh, the target or the material that we are evaporating and the sample. So it should directly evaporate from here and go and stick on the sample. Though that is not perfectly possible, but that is the ideal thing we want, and that is why we create the least number of molecules available there. So in this case, and we keep this sample and the target very close so that these molecules can easily go to the target directly. So it will be all of the above. Okay. Next is ALD. Can anyone tell me the full form of this?
It is a atomic level deposition.
Atomic layer deposition. So here the precision is of one single atom layer with precision of one layer of, like if this is our substrate, here single layer of atom at once, then another layer. This level of precision is attained in ALD. So can be deposited, can be used to deposit a film with minimum thickness and better precision. Is it true?
It's true, no?
It's true because here from the name itself it can be done one atomic layer at a time. Okay. Now, why is argon gas used during sputtering of metals? Because it is an inert gas and does not react with the target. It bombards the target. It can be used as carrier gas for other gases for the process, or all of these. Anyone? Yes.
Only A.
It is inert gas, does not react with target. That's fine. Okay. Anyone else? Anyone? Anyone else would like to add something? There's, let me ask someone. Mm, Aruloli, are you there?
Yes, sir.
Yeah. So can you add something? Like which one of the following should be correct?
I think the argon gas is an inert gas apart from the diatoms or anything. It's an inert gas, the diatom.
Okay. Like A should be correct, right?
Yes, sir.
And what about B and C?
I think B is also correct, sir. It bombards the target.
Okay. So like if it is like that, why we are not going for some other gas? It is like inert gas, that's fine. So even nitrogen can be considered a bit inert. There are other xenon, radon, like there are a lot of inert gases. So why argon? Does anyone have idea? Let's ask someone else also. Swati, are you there? Yes, Swati, Varsa, or anyone? Yes, please.
I feel it's all of the above.
All of the above. That's Very true. But why argon? Like, why can this not be done with something else? Carrier gas can be any other gas also. Any other gas
Due
can
to its
also be
high
done.
atomic mass,
Yes, very true.
due to its high atomic mass,
Yes, very true.
I think.
That uh, sputtering, when we talk about, I think, yeah, if you see this diagram, the sputtering works like uh, if we are throwing, if there is a mud and if we are throwing a stone in it, it will like it will sputter some particles from there. And if we are throwing a small stone, what will happen is that it may not have that much of strength to make the mud go away, like get sputtered easily. And if you are putting a very big stone, also it may not sputter that much. So not we don't want a very big particle, like almost bigger than our target, uh, or we don't want a very small particle also that will not be able to sputter. So we want a heavy particle, a bit bigger, but not very big. And for that, argon is the most preferred one in case of sputtering. Argon is the one. Argon has inert property, so it will not take part in any kind of reaction, but it will easily be able to knock out the atoms or particles from the target. So it is like it is coming, argon is coming, and then here a plasma is formed. Plasma is formed either using positive and negative, so that will be DC sputtering, or either RF frequency, so that will be RF sputtering, or magnetron. In all the cases, some plasma will be formed. Plasma, and in this case, what will happen is that argon will get positively ionized, and then it will move fast towards our negative target, and then there it will hit it. When it hits, it is creating a very similar effect to when we throw a stone in mud, and then some something is getting sputtered. So molecules will get sputtered here and there, and we are keeping the target very close to it, as well as moving for uniformity, and then this will get deposited. In this case, no heating is required, no no chemical processes involved. So you will see, this is from one of my work. You see, like how this is it visible? This small particles, how they are deposited. Are these
Yes, it is
particles
visible.
visible? Yeah. So you see that actually I so zoom it. Just yeah. If you see, if okay, it is taking some time to read. Yes, you see very small particles. In this case, it is PD, I think. Yeah, palladium. Very small particles of PD is scattered throughout the surface. This is almost you can say like just this thickness is in nanometers, less than 100 nanometer. Okay, so very thin, you can say just 4 or 5 layers, atomic layers has been sputtered, and this is much uniform compared to thermal thermal evaporation or e-beam evaporation. That is why sputtering is used. And if you compare the size, weight of the argon with PD and this, actually PD is heavier. But if argon was not used, some other like nitrogen or hydrogen was used or oxygen was used, it would not have been able to knock it out, first thing. And the second thing is that it might get involved in some kind of reaction, like it might be creating PD halide or PD oxide, such kind of things. That is why this being inert is one of the advantage, very true, but there are other inert gases also. It bombards the target. This is one of the greatest advantage that we have with argon, and this is very well said that this is due to the molecular mass of argon. Okay. So, which of the following techniques gives better results? Core sputtering, DC sputtering, E-beam sputtering, or magnetron sputtering? Anyone?
I think E-beam.
E-beam. Okay. Anyone else? E-beam sputtering. Okay, one. Anyone? Any other answers, or someone would like to support this answer? Yes, I think Swati, you are you there? No. Yes, E-beam, and please be ready with Y also. Okay. Y E-beam or any other. Okay, let's before going in that, let's see the difference. Then I think you will be able to uh, visualize it properly. So, what is co-sputtering? It is when we are using more than one target at the same time. Like suppose we are using silicon and copper target or carbon target. Okay, and then we are depositing both of them at the same time. Either we can be using RF, DC, or whatever technique we have. Then comes DC. Here I have missed it. DC sputtering. DC sputtering is the same one, just like I showed that my work also, that was DC sputtering, where we have very high negative voltage in the target. Target is the one which contains our material, and substrate or sample is the one on which there will be deposition. Okay, so negative to the target and positive to the substrate, like there, if a field is connected using positive and negative voltage, negative and positive voltage. Okay, then if we talk about e-beam, there is nothing called as e-beam sputtering. I could not find one. Okay, so it is e-beam evaporation, in which case the material is evaporated using an electron beam. The electron beam will heat it and then make it evaporate. Okay, so that is e-beam evaporation. It is not e-beam sputtering. Okay, then is the magnetron sputtering, in which this whole plasma thing, like we created here, it is created using very high magnetic field, and a high magnetic field will again be created using current only. So it is DC magnetron sputtering. So a high magnetic field using DC. In this case, it was just electric field. So here, electromagnets will be used to create the field, very similar to DC sputtering, but in this case, it will be, instead of electric field, it will be magnetic field. So from this, can you then which one is the best one? Which one will be the fastest one? Anyone? Yes. Hello. Are you able to hear me?
Yes, Vikas. Yes.
Yeah. So now can you guess which one will be the best? Like which one will give the best yield?
Still, I go with electronic sputtering only.
But there is actually no electron beam sputtering.
Yeah, you told there is a electron beam evaporation.
Yeah, it's electron beam
Basically, I heard
evaporation.
somewhere, Vikas, that
Yeah.
it is for the sputtering of insulating materials.
Yes. I like it is actually nowadays being talked about, but it is still like what I have studied and all. It is still like mostly considered in part of this one evaporation techniques.
Yeah, yeah,
Yeah,
you're right.
so it is still not being categorized as sputtering technique. And if
Yeah,
we are
yeah,
talking about sputtering, I am ignoring this altogether because it is still not considered sputtering technique since our question is
yeah, yeah,
about sputtering technique.
yeah, yeah,
So if we are comparing the sputtering techniques in this case, so in all the cases we see that there is only one target that is being used. Uh, Even in here, one target. But in case of coarse sputtering, we can use multiple target and sometimes even multiple targets of the same material. So we will have better yield, almost twice or thrice according to the number of targets we are giving. So instead of one single source, we are using multiple sources together, sometimes RF and DC or RF and RF. Okay. That is why the yield is a bit higher in case of coarse sputtering. But coarse sputtering will certainly require more number of, you can say, power sources, either DC or RF. So the yield is higher in case of coarse sputtering, but coarse sputtering will have other problems like the cost will increase as well as power sources will increase. We have to take care that there is no interference. There are other factors involved, but the yield will be higher in case of coarse sputtering because it actually involves this DC, magnetron, and RF sputtering, and it is multiple sputtering at the same time. So the yield will be higher in this case. Now let's
it's
come to,
nicely explained.
yeah.
Right.
So the mask. Let's come to lithography. Okay. So you must have seen at the last of the this week lectures there was something called as lithography being taught, and I also said that lithography is the technique that is having the most important part in case of microfabrication. Okay. So whenever we talk of lithography, especially photolithography means where we are using light as the source of exposure. Light is the thing that will actually pattern. So there is something called as mask that is uh, between this light and our sample. And sample will have, let me use some colors. Okay. On the top of sample, we will have HTMS and PR coated as we saw earlier also. And then this light will go through this mask, and the pattern made on this mask, whatever pattern is there, according to that pattern, we will have the exposure below. So this is the mask. Now, okay. Yeah. So this is the mask. Now it is saying that a mask having dark features and transparent background. So the mask will is this. So it is all transparent and it is say having a feature like this. And the feature is dark through which light cannot pass. What is this kind of mask called as? Is it a dark field mask, bright field mask, gray mask, or black and white mask? Yes,
It's a dark field mask.
dark field mask. Okay, anyone else?
Bright field marks.
Bright field mask. Okay, why bright field or why dark field?
So most of the area is transparent, so it's bright field
Yeah.
marks.
So whenever we are talking about field, we are talking about the maximum area. So in this case, since the maximum area is exposed, so it is called as bright field mask. So in general, we can say we have two type of mask, light field or dark field. And its application depends on the pattern we are trying to make as well as the resist we are trying to use. Okay. Similar to this mask type, there are two type of resist also, positive and negative. And in case of positive, what happens? The exposed area get dissolved or the unexposed area get dissolved. Yes. So to just remember it, if you remember one, like light field mask, remember that if we use it with positive photoresist, it will give us the same pattern. Okay. If we use this over a positive photoresist, the pattern that we are getting after developing, we will get the same pattern. That means the exposed area that is on which light will come area will go out. Okay, it will dissolve. So if we are using this mask, like in this case, it is a dark field mask because this one is chrome and the pattern area is open. So then you see that this part was exposed to light, and that is why it got dissolved and we get the other part. Whereas if we have a negative resist, in negative resist the opposite happens. The exposed area remains and the other things dissolve in the developer. Okay, and exposed area will go out in developer. So if we have a negative resist, it will have the opposite effect. Okay, so either to make opposite patterns, we can either play with the resist type or we can play with the mask type. Fine. Any confusion in this?
No, Vikas. No.
Yeah. So this is a bright field mask, and whenever we are talking about the field, though it looks a bit confusing that we have the feature, the main thing is dark. Okay, so it looks like it should be dark field, but whenever we are talking about field, we are talking about maximum area. Maximum area that is available. So if the features are dark, the maximum area will actually be bright. So it is bright field mask. This terminology are a bit confusing, so just to make it clear. Okay. Now let's come to a very basic question. When we started this whole course, we started this whole course by cleanliness, like clean rooms and these things. So what does the class of clean rooms denote? The pressure inside the clean room, or the number of people permitted inside the clean room, though this is also regulated. Okay, the lifetime in year for faithful operation of the facility, or the number of particles. Yes, anyone? Yes. Aruloli, are you working in some pharmaceutical or biotech? I think you said last week, right? Hello, are you there?
No, sir, I'm not working here.
Yeah, what you are saying, I am not able to hear you.
I'm not working. I'm not working.
Okay, like you are from biotech, right?
No, sir, my background is electronics.
Electron. Okay, okay. Someone in the last class, I think said biotech or something. Anyone who would answer? Then electronics people also, I think they also work in clean rooms, right? Anyone?
Because is a D is the number of particles per
Yes,
cubic feet.
number of particles. Very fine. Yes.
है ना?
I think I have not put, okay, that I have not put. Actually, the first thing is that whenever we are making any doing any kind of microfabrication, there is a very interesting question I will put someday, that uh, there is different class of clean rooms starting from class 1. Like there are two standard way. One is the American one is ISO. In American one, they go by per cubic feet, okay, and in ISO one, they go by per cubic meter. How many particles of a standard size less than 0.15 micron, or how much is permitted inside that room? And then there are classes of clean room: 1, 10, 100. I think in India we don't have class 1. I am not very sure. Okay, but we have class 100. I think in Siri we have ISC also. I think there is a class 100, class 100, class 1000, class 10,000. These are the classification. Even the pharmaceutical industry or biotech, that is why I was asking. They also use class 10,000, 10,000 clean rooms. So this determines, like these are how much particles are inside that clean room, the maximum allowed particles. And for that, we have to do a lot of things, like the air has to be purged regularly, cleaned, and then put inside. The humidity has to be maintained. The pressure should also be maintained. Number of people permitted, as well as uh, how the person will enter, how the person, anyone is not allowed to wear normal clothes. Like you have to wear some covering, apron, and everything is to be covered. Mouth, face, all these are to be covered. These are taken care. And why is this done? So I will someday show a question that if we have a clean room, suppose we have a class 100 clean room, okay, and we have a wafer of say 3 inch, 2 inch, 3 inch, 4 inch. These are the uh, common standard wafers, and there is a continuous flow of uh, air over it. It is kept exposed in a class 100 clean room. So class 100 is like very good clean room. Still, uh, how many particles will get accumulated over this wafer will surprise you. If you calculate how much is the flow and everything, it will be around like 700-800 dust particles will get accumulated over it. So even in clean room, these wafers and everything are kept very well. Like they have to be kept packed and all those things. So a lot of precaution, like if we are calculating that all 100 particles are actually allowed, they are the maximum allowed ones. Okay. So it is very important to have all these processes inside clean room, and having these processes inside clean room will increase the probability of having good devices. Because if we say 700-800 small particles of zero point 0.5 or less than that micron, if we think it is fine, not an issue. But when we see the size of actual transistors, like in this one single wafer, how many transistors can actually be made? If we are talking about sensors, it is fine, even fine, because we are going for bigger ones. But when we are making very small transistors, like millions of transistors on one wafer, in that case, a single dust particle will also matter. That is why these clean rooms are very important, and there is a class of clean rooms. I'll In the next class, I'll try to put the table how these clean rooms are classified. And I think later on in the course also you will see how a clean room facility is there in ISC, how they are maintained. And yes, Dharanjay. Yes.
Vikas, I do have one question.
Yes.
We have observed so many times in the pharma industry that they are
Mm.
keeping so many doors before
Mhm.
entering into the medicine room or the plant.
Yes, yes,
So, is it the way to increase this class? And
yes.
number two, only purging is the way to increase. The class of the room.
There are many more ways. Like
Okay.
I have also like this backend facility. I also am not very aware of. But yes, I have seen like class 100 clean room. In that, they even maintain a laminar flow of the air
Yeah,
inside.
at the door side.
Yeah, not just door side, the whole room. And in fact, no person can enter that. Only uh, hand gloves are allowed. Like that glove box is allowed in that area. So no
Fine.
person is even allowed in that. So I think there must be some more things like flow and other and HEPA, HEGA filters. These are common, but I'm not very sure about that part. Like what is happening in the back
No.
end. Yeah.
But
But
still, I do have one question. Is not
yeah.
directly related to this clean room, but I just
Yes. Yes.
recalling the about the silicon bowl.
Mhm.
Whenever actually we are talking about the one is they can say smooth surface, another is a rough surface. Usually we are
Yes.
using for the device
Yes.
fabrication.
Yes.
So whenever we are cutting the bowl, so are we getting uh, that smooth
Roughness.
surface
No,
and
no. We are getting the rough surface.
rough surface both the side, ne?
Yeah. Yes. Both
And
the
then we
side
have
we are
to
getting. Yes. Then we do polishing kind of thing.
fine. Okay, thank you.
Yeah, then some like very fine polishing is done, and that is why you see that generally we have one side polished. When we want like both side polished, it will cost more because that polishing will
Yeah,
cost.
yeah.
So it is the number of particles.
Vikas, one more question. Vikas,
Yes, sure.
how we can get these bowls? From the market. We are purchasing directly bowl or with the
No,
certain techniques we are creating these bowls. Jocro select techniques.
no, like that mostly like India, we don't have any such facility. Uh,
Exactly.
in India, we are directly buying this wafers.
Yeah.
Like before wafer, we don't have any kind of technique in India at present.
So we are not
So
buying bowls.
no, no, not balls. We are getting directly wafers. What kind of wafer? And that is the thing that the government of India is trying very hard, that we have this semiconductor fabrications in India, so that
Yeah.
the cost will decrease a lot. We are buying it at a very high cost, I can say,
Yeah. Yeah.
because we
Yeah.
don't have
Thank
the
you.
facilities there. Okay. So in the deposition, PVD stands for. I think I have already answered this. So
Is
anyone?
a D physical vapor deposition.
Physical vapor deposition. So As we discussed, there are two kinds of deposition, physical and chemical. Physical, in which there is no chemical reaction involved, and chemical vapor deposition, or CVD for short, it is having chemical reactions involved. Precursors are involved. Okay. So based on this, the next question: which of the following is not a physical vapor deposition technique?
ALD?
ALD. Good. Why ALD?
Because that is a chemical vapor.
Yes. There, so if you see the process at first, it will look like a physical vapor deposition. But here, precursors are put, and then the deposition is happening. But very similar to, like the process is very similar to sputtering, like where we are creating plasma and all. So it looks like it is a physical vapor deposition, but it is actually a chemical vapor deposition. And in this case, the precursor are not directly put like other CVDs. Like other CVD, we have mostly aqueous tube closed from both the sides, and we will have the chemical here, the target here, and then we will flow some gas that will help this reaction, and then it will carry and deposit here. But in this case, this is very sophisticated, closed kind of structure, but still there are precursor here. And the precursor also looks like a small gun, and you have to fit it and do that. Okay. So ALD is not a physical vapor deposition, it is a chemical vapor deposition technique. Fine. Okay. Transfer of pattern into a material after deposition in order to prepare for etching is called etching, patterning, PVD, or CVD.
Is a patterning, ne?
Patterning, yes. Since it is transfer of pattern, it is patterning, or also very similarly called as lithography. Okay, and you must have heard litho means stone, and graphy means cutting. So it is like stone cutting or structure cutting. So it is patterning. Okay, now is dipping substrate into chemical solution that selectively removes material. What is this called? We are removing material, so certainly it is etching. Okay, but what will it be called? Dry etching, wet etching, both of this, or some other kind of etching?
It's wet etching, ne?
Wet etching. Since we are dipping, simply it is dipping something in a chemical solution. It is wet etching. Okay. And now the opposite of it, if the material sputtered or dissolved from substrate with plasma or gas variation. Okay. Here we are not putting inside a chemical. Like first processes, we have some chemical which is very selective to the thing that we want to remove, and uh, like it will not etch the pattern. We dip, so we dip the wafer with the pattern made, and so it will remove the other part. It will leave the things that are below this pattern. So that is wet etching. And in this case, we have the wafer with pattern, or the pattern like may not be there. Then we will decide in that how this is done. But mostly there will be pattern or mask over it, and then we are creating plasma or some gas, different kind of plasma of the different kind of gases. So what is this called? Anyone?
Is dry.
Yeah, it is dry. Since we are not using chemicals, here it is called as dry etching. Okay. Now, what is lithography? After doing all this, to a very basic question, what is lithography? Yeah. Process used to transfer pattern to a layer on the chip. Process used to develop an oxidation layer on the chip. Process used to develop a metal layer on the chip. Process used to produce the chip.
I think we go for A, no?
Okay. To transfer pattern to a layer on the chip. It can even be an oxidation layer, it can be a metal layer, it can be anything. If we are patterning, we can use lithography. Okay, so
Yes.
we cannot say that it is oxidation layer or anything. It is a very general process and very important process. Like I am repeating this again and again because you will find lithography a lot. I think the next week will be week 3 will be dedicated on lithography maybe. Okay, this is a very important part and uses a lot of ways and a lot of things, very precise things. And if we miss a small step, a lot of changes will happen in our fabricated devices. Okay. Which of the following is a primer which is coated to improve the adhesion of photoresist on the surface of the substrate?
HMDS?
HMDS, right? So this is the same thing, like rephrase that primer. Remember I talked about primer, and what does the primer does? It creates a addition layer. It also smoothens the surface as well as it creates a very good layer so that a thin layer, like when we are coating the photoresist, it is not like we are coating by a brush. We are putting it like putting it above the wafer through a dropper or any other way, and then we spin it at very high speed, like 2000, 3000, 5000 rpm, and then it just spreads. So in that case, we want that it should be smooth, but not so smooth that everything goes away. Okay. In fact, this HMDS is also coated like that, but since it is uh, thinner compared to photoresist, it will create a very thin layer of thin layer that will actually help the next layer, the photoresist, to adhere. Okay, so HMDS. Which gas is used to dry the wafer? You must have
Nitrogen.
nitrogen. Yes, you must have seen that. In fact, in every step, by default, what we write is that like deirins and nitrogen flow. This is something
Yes.
that we generally write everywhere. Rinse
Hmm.
with DI water and then do the nitrogen
Blow with
flow.
nitrogen.
Blow with nitrogen. Because one thing is one very uh, specific reason is that nitrogen is the cheapest gas that does not react much, and it is available in the atmosphere, and that is one of the reasons, and it is very easy to prepare. In fact, if we just bottle the gas present near us, clean it, it becomes nitrogen. We just have to remove other gases. 70% is already nitrogen. Dry gas also we use, that is mostly nitrogen. So that is used. Anyone would like to add what is this DI water, deionized water? Anyone knows? Is it the RO water or something else?
I think it's a double distill, but I'm not sure about.
Okay. Anyone else? Versa, Aruloli, anyone? Yes, Versa, are you there?
Yes, sir, but I'm not sure.
Okay, you can attempt, not an issue. You can try like whatever is coming to your mind, then we can discuss. Yes, Aruloli, are you there?
Yes, sir. I think it's a pure water. There is no other molecules.
Yes,
Pure.
very right.
You don't have that kind of water. I don't know.
Yeah.
Pure.
See, first thing is it should be clean, distilled. This is fine. But along with that, the water we are using, even this RO water, no, there are still some ions. See, when we are talking about deionized, this is ions like calcium, magnesium. These ions can be there. Okay, and these ions have the like they are fine for us when drinking and all. But whenever we are talking about these processes, actually we should have no ions because these ions will actually adhere to the metal or whatever structure is there, and they can create some effect. What effect they can create is that first that since they are ions, they can increase or decrease the conductivity of the surface of our structure, our wafer, and this. That is why we need to remove them. And this is removed very similar to RO, like what is done in RO, and distillation process is also done again and again. Uh, like two, three processes are done, and then we get the deionized water. But its lifetime is very less, maybe like 3 hours, because there are many ions in our environment also. They will very easily, since there will be a gradient, nothing is there, so they will try to get inside and they will mix up. So this deionized water is a very important part, and in fact, in many other industry, pharma and all of, so ideally, deionized water should be used, but mostly since some in some industry you might not have that availability, so people go for ultra pure RO water and this thing, or HPLC water. But this deionized water is the one that is used in case of semiconductor industry. That there should be no ions. In fact, this the resistance of this water is considered to resistivity is considered to 1 mega, like 10 is the normal accepted, but ideally it should be 18 mega ohm per meter cube. This is the resistivity of deionized water. Fine. Any doubts still here?
S- Now, because for that
Yes.
we do have special equipment. I mean, what kind of,
Yes,
can you
there
narrate?
are, yeah, there are deionized plants there. Small,
Okay,
just
are
like
they
RO
costly?
plants and all. Not very costly, but yes, there are. There are like
I mean,
a bit costlier than RO. I think double than RO, but yes, there are like deionized plants there.
okay. I mean, for I mean, washing of our glasswares in a laboratory, should we use this deionized
Yes,
only?
yes. Ideally, we should be using this. For washing the, at least if not washing, then after washing is done, it should be rinsed with DI water so that all the extra molecules, whatever has come from city water, like that is removed.
Usually, we are cleaning our glasswares with acetone. So, is
Yes,
it fine?
yes, fine. But after like acetone, we also generally like after acetone, since there will be stains. If you are washing with stains, you will see that acetone. You will see there will be some white stains if you
Yeah, yeah,
don't wash with
yeah.
DI water after that. So that
Okay,
stains, and actually that stain is again a problem. Like
yeah,
especially in semiconductors, it is a problem. That is why, uh, like after that, we go for DI rinsing and then nitrogen blow, or like
fine.
we invert that and put on a heater, like what we do, this plate, hot plate. Yeah, we
Hot
put
plate.
it, yeah, we invert it and put it on hot plate at maybe 80 to 90 degrees Celsius, and then gradually it will evaporate, and then we invert it back, and whatever is there it will evaporate, so like it is fully clean. Fine.
Yeah, thanks.
Yeah. Yes, any other questions? Okay. For any questions, I'll be here for some time. Yes, you can ask questions.
Sir,
Yes, Vaikram.
there was a question in the assignment.
Mhm.
S1813 is a photoresist that is commonly used in
Yes,
photolithography.
yes, yes.
And it was asked, what does the chemical number 13 stand for? Uh, there was no explanation given in the video, nor I was able to find any in the net also, so I just started.
Okay, and what are the options given?
Uh, Process temperature of 13 degrees Celsius, resist thickness of 13 nanometer, resist
Mhm.
thickness of 1.3 micrometer, none of the above.
Mhm. Okay. Uh, See, the number actually signifies a lot of things. Okay. Whenever we are buying register, though I know the answer, but I will not give you directly since the like the time has not like the last date is still there, right?
Tomorrow, I guess. So.
Yeah. So do one thing. It is generally related to this that this number will generally represent the rotation speed, and this will represent the corresponding thickness. Okay, you will have to find the unit of it. Okay, I have given the hint. Fine. You do one thing. You just read the dataset of this. Search for dataset of S1813 microresist. Okay, microresist
Okay.
photoresist. You will if you can find like at 18 something rotation speed, what is the thickness? I think you will get the answer. Fine.
Yes, sir, I'll do that.
Yes. Anyone else have any question?
Sir, and none of the evaporation techniques will be used to deposit a layer. No, sir. Deposition is different from evaporation, right? If I'm not wrong.
See, evaporation is like you are evaporating something from here and then you are depositing here, like thermal evaporation method, right? Here you have metal, say gold. Okay, you are hitting it to such a high temperature that it evaporates, and when it evaporates, something is like your sample is put here. Okay, so what it will do? It will go and stick there. So it is like deposition by evaporating your material. Fine.
Oh, okay, sir.
Yes. Any other question? Okay, so that's all for today. See you all in the next class. It will be the same time, and all this class will be recorded and available for you in the YouTube channel. Fine. Thank you all.
Thank you, Vikas, for nice presentation. Enjoyed a
Thank
lot
you.
and learned.
Yeah, thank
Thank you. Good night.
Thank you, sir.
you. Yeah, thank you.